Hello everyone and welcome back to the channel. In system design, not every task needs to be processed immediately and synchronously. In fact, trying to do so can quickly lead to bottlenecks, unresponsiveness, and system crashes. This is where message queues come into play. They are fundamental building blocks for building scalable, reliable, and decoupled distributed systems. In system design interviews, discussing message queues intelligently showcases a deep understanding of asynchronous communication. Today, we are diving into their core concepts and why they are so vital. Okay, so first let's try to understand the problem. I need my pen here. So let's say that we have a client or a customer that uses our app or our server, and our server, it's an e-commerce. Okay, so to understand the challenges that message queues are designed to solve, we need to imagine this typical e-commerce order placement when a user click buy. Okay, we have 4 or 5 problems that we will talk about. First, we have asynchronous bottlenecks, like if the processing of the payment, updating inventory, sending an email, and logging the order all happening synchronously in one go, one by one, the user has to wait for all those operations to be completed. A slow payment gateway or an email service can block the entire process, making the user interface unresponsive. Number 2, we have a service coupling. The order service would be tightly coupled to the payment, inventory, and the email services, needing to know their APIs and handle their failures. Number 3, we have a problem with reliable and durability. What if the email service is down temporarily? The whole order process will fail. It cannot be processed at all. We have also workload spikes, like what if thousands of users try to place orders simultaneously during a flash sale? Your services might get overwhelmed. These problems highlight the need to separate task creation from its execution. Okay. So, what is a message queue? A message queue is an asynchronous communication pattern where senders, called producers, place messages which represent tasks or events onto a queue. Receivers, called here a consumers, then retrieves these messages from the message queue to process them at their own pace. How does this work? So we have here a producer, okay, and we will have here our queue, which will have the messages that the consumer C1 and C2 will pull. So when the producer sends the event or a message to the message queue, the consumers can pull them and get them. So again, a message queue is an asynchronous communication pattern where senders, called the producers, place messages which represent tasks or event onto the queue. Receivers, which here called consumers or workers, will retrieve those messages from the queue to process them at their own pace. The key concept here is decoupling in time. The producer doesn't have to wait for the consumer to be available or to complete the task. It simply puts the message on the message queue and move on. Think of it like a never-ending to-do list or an inbox. Okay. You add tasks to the list and someone else picks them up later when they are ready. This separates the responsibility of creating a task from execution it, okay? Executing it, not execution it. Okay, so let's take a more deeper look to understand exactly how does it work. So a message queue system relies on central components, which is a message broker. This is the specialized service that manages the queues and messages flow. Popular examples, I guess, will be like RabbitMQ, Amazon SQS, or Apache Kafka. So let's try to understand how does it work. So first we have the producer. Everything starts with the producer. The producer here, a producer creates a message, like for example, send an order confirmation email or process a payment, and sends it to a specific queue. It will send it to our message queue. Okay. So right now we have this message here. The broker will store this one. So the message broker receives the message and retrieves it durably in the queue. This persistence is crucial for reliability. The message won't be lost if the consumer isn't immediately available. Here we have, let's say that we have two consumers here, C1 and C2. The consumers, the consumer or a consumer or the consumers, which is a separate applications or worker services, will pulse or receives push messages from the queue when it's ready. Consumer process and acknowledge this one, like the consumer will process the message, actually, like for example, sends an email or something like that. Once processing is successfully, the consumer sends an acknowledgement back to the broker. And after that, the broker will delete the message. Like upon successful acknowledgement, the broker removes the message from the message queue. If an acknowledgement isn't received, the broker might re-queue the message queue for another consumer to pick up later. Okay, this allows for robust asynchronous task execution. Okay. Why message queues matter in system design? So message queues are incredibly powerful for several reasons, making them essential in modern distributed design system. First, asynchronous processing. Long-running or critical tasks like sending emails, processing images, generating reports don't block the user interface or critical applications flow. This dramatically improves systems responsiveness. Number two, decoupling. Producers and consumers are completely independent. They don't need to know about each other's availability or internal logic. This makes system much easier to develop, deploy, and maintain. Number three, buffering and load leveling. Queues acts as a buffer for incoming requests. During workload spikes, messages are buffered in the queue and consumers process them at their own steady pace. This prevents back-end services from being overwhelmed and crashing. Next, we have reliability and durability. Messages are represented by the broker until successfully processed and acknowledged. This prevents message loss even if producers or consumers fail temporarily. And next, we have scalability. Like producers can scale, like producers simply send messages and move on, unlocked by consumer speed. We can scale consumers as well, like you can easily add or remove consumer instances to match the processing demand if the queue grows deep and we add more consumers. Also, we have fault tolerance, because if a consumer instance crashes during processing, the message can be requeued and picked up by another consumer. So the system is fault tolerant. Next, we have order processing. So some queue systems like Kafka partitions or FIFO queues can guarantee messages order for specific use cases, which is crucial for certain workflows. Okay. So next we'll talk about some challenges and considerations when working with message queues. The first thing I would say in the complexity, like you are adding a new critical component, which is the message broker, to manage, monitor, and scale. Number two, latency, like there is an inherent small delay for messages to travel through the queue, not suitable for truly real-time synchronous interactions. Number three, debugging. Tracing the end-to-end flow of message across services can be harder, can be really harder, to be honest. Number four, message delivery semantics. Understanding guarantees, understanding guarantees is crucial. And handling idempotency in consumers become paramount, and this is not easy at all. Also, we have poison pills, like mail-formed messages can repeatedly cause consumers to crash, requiring dead letter queues and error handling strategies. And I will create a video that talks about what is a dead letter queue, because it's a pretty important concept in synchronous communication and system design. Okay, how you talk about it in system design. So in system design review, I would say you need to bring up message queues whenever you have asynchronous tasks, long-running operations, or a need to handle workload spikes. contrast it with synchronous API calls, discuss its benefits for reliable and scalable, and highlight the changes like eventual consistency and need for idempotent consumers. Naming specific technologies like RabbitMQ or SCQS demonstrates particular knowledge. So yeah, that's it for this video, and thank you for watching this video, and see you in the future, guys.